join us on the third series of seminar of this semester in the graduate program on chemical engineering. So this afternoon, I have the pleasure to have on board Dr.Charline Fouchier. I met Dr.Charline back in 2015 in the US during a conference that we were attending. We had the time to discuss some of the research that she was doing and also the research that we were doing in Brazil. So it was very pleasant time, very interesting topics. And then we met a couple of other times in the same conference. So I'm very happy and very glad to have you here, Charline. Thank you very much for accepting our invitation. Dr.Charline is a postdoctoral research at the VTI, which is the Von Karman Institute in Belgium. She completed her PhD this year on the investigation of pollutant dispersion driven by condensed-phase exposure in a complex environment. She has a master's degree in industrial safety from the École Nationale Supérieure de Mindales, a master's degree in environment and urban risk from École Nationale Supérieure de Saint-Étienne in France, and a postgraduate research master in fluid dynamics from the VTI in Belgium, during which she won the Excellence in Experiment, the award on excellent research for her work on blast propagation in an urban environment. So, and again, Charline, it's really a pleasure to us to have you here. And now, without any further ado, it's up to you to start your presentation. Thank you.
Thank you very much. Thank you for the introduction, and thank you for receiving me today for the talk. It's really a pleasure for me to be here, and thank you for attending this presentation. So today I will present you a bit my PhD work on the investigation of the pollutant dispersion driven by condensed-phase explosion in urban environments. So safety, it's a discipline which needs to constantly evolve with our society and our industrial activities. And in 2001, Kroll highlighted 3 main accidents that could occur in an industrial plant: the fire, the explosion, and the toxic release. And based on past accidents, he could estimate the probability of occurrence of these accidents, the potential for fatalities, and the potential for economic loss. And even though the fire shows the highest probability of occurrence, it's actually the explosion and the toxic release which show the highest potential for fatalities and economic loss. You can see here an example of the destruction that can be caused by an explosion. This is the resulting effect of the explosion of AZF in France in 2001. So as investigating the explosion is a safety concern, but also a security one. We can see in our society growing more and more the terrorist threats, and we have really sad example of this threat. So, for example, the attack of Brussels in 2016, or of course the attack in New York in 2001. The last accident that you might have seen actually occurred in Beirut this last August, with the explosion of storage of ammonium nitrate. So 2,700 tons of ammonium nitrate exploded this day and created a lot of damages. So during this presentation, we will try to come back to the images that we could see in order to try to understand the phenomenon that we can observe. So an explosion can be defined as an energy release sudden enough to lead to a local accumulation of this energy. And this energy will dissipate in various ways. We will have the generation of heat flux, so a fireball, the propagation of seismic waves underground, the propagation of a pressure wave, also called blast wave for strong explosions in air, that will lead also to blast winds, so strong winds, and also some projection of missiles. In case of an explosion of an heterogeneous charge, we will have also to face a pollutant release. When the explosion occurs in urban environments, the presence of buildings around the explosion will actually reduce a lot the effect of the heat flux and the effect of the missiles on the environment. However, the configuration will impact in a more complex way the propagation of the blast wave and the pollutant release. So that's why in that project, we really focused on these two phenomena. And during this presentation, I will more focus on the pollutant release. So in 2004, Brown described the explosively driven dispersion into three main stages. The detonation stage, where the explosion will be led, the dispersion will be led by the explosion. The buoyancy puff rise, where the dispersion will be led by the thermal effect, and the passive dispersion. So in general, the simplified models are really the key to ensure a good safety in the industrial plants, as they allow a fast first estimation of the risks. And in the literature, we can find simplified model dealing with the dispersion, but only taking into account neutral buoyancy dispersion or a dense gas. So we could use a neutral buoyancy model in order to simulate the dispersion, but we need to know how to simulate the source term to simulate properly the whole dispersion. So in the literature, we could find some work on the explosively driven dispersion, but the work mainly focused on the first millisecond of the dispersion, where mainly is the explosion that will lead the dispersion. So here you have the example of the investigation of Frost in 2012, who investigated the dispersion of solid particles until 15 milliseconds. And here you have an example of the investigation of Jenkins, who investigated the position of the particle fronts regarding the position of the blast front. And he observed that actually at the beginning of the explosion, sometimes it can happen that the particle fronts propagate faster than the shock. And we see after an inversion and the shock will propagate faster. And if we come back to the images of Beirut, it's actually what we can see. So here is a slow motion of the explosion. So you can see here the brown cloud that is mainly the combustion products of the ammonium nitrate. And after you see a white cloud here, that is actually the blast wave. The blast wave, normally it's invisible by eye, but we can see its consequences on the environment. So you can see first the disturbance on the sea surface that is actually the positive phase of the blast wave that you can see here. And the plume is actually produced by the negative phase of the blast. So we will see the blast wave a bit later, but the negative phase here will condense the humidity of the atmosphere and produce this plume. So we can really visualize the propagation. So if we come back, really we see the particle front, the pollutant front that is propagating faster, and after we have an inversion. So the objective of the work was to investigate the dispersion from the beginning of the dispersion, just after the explosion, to the passive dispersion that couldn't be found in the literature. And the experimental data will be used in order to validate future numerical models, simplified numerical model, and will be used also to understand better all these phenomena. So the main challenges that we had to face, first of all, is that the explosively driven dispersion is really contains a large dynamic range. So we have really high velocity just after the explosion and really low at the end. And we have also a different scale. The plume is really condensed and small at the beginning and will disperse and get larger and larger with time. Of course, experimentally, it's really challenging because it's difficult to access due to the presence of the explosion. And it's a transient phenomena, so it's always more difficult to analyze. And from our knowledge, actually, this work is pioneer, so we don't have really some help from the literature. So during the presentation, I will first give you the experimental setup that we used to investigate the dispersion, and then the methodology that we applied. First to characterize the explosives that we use, and then to characterize the dispersion. Then I will give you the experimental results that we had based on the contour analysis of the plume, the large-scale particle image velocimetry technique applied on the plume to extract the velocity field, and the miscattering technique to extract the concentration field of the dispersion. Then I will give you a short talk about the application of these techniques on other challenging flows, and I will give you a conclusion and some perspective. So first, the experimental setup. So the test had been conducted in the wind tunnel, subsonic wind tunnel of the Van Karman Institute in Belgium. So here you have a picture of this tunnel. This tunnel has a rectangular section of 2 meters wide, 2 meter high, 3 meter wide, and 20 meter long. And we can simulate flows from 2 to 50 meters per second. Here you have a picture of the inside of the test section. So we use some roughness elements in order to reproduce the atmospheric boundary layer. In that case, here is plastic cups. So you can see here an example of the velocity profile that we obtain using these roughness elements. So as you can see, the velocity increases with the height. So this is typical to an atmospheric boundary layer. And depending on the height of the roughness element, we can simulate an atmospheric boundary layer for typical to an open area, so in the sea, a forest area, or urban environment. In that case, always the atmospheric boundary layer will be neutral. And in our analysis, we used actually high cups to simulate an urban area, so high atmospheric boundary layer. And yeah, we used the reduced scale of 1 to 200. Inside the test section, we can go from 1 to 200 to 1 to 350. So we installed a test table of 2.8 meter diameter that you can see here. So it's made in wood. And we used a metal plate in the middle in order to protect the wood from the explosion. So we used here, as said, a reduced scale of 1 to 200. So this is compatible to the reduced scale of the wind tunnel, but also the scale of the explosive that we are using. And to simulate the dispersion, we used micro-sized talc powder that we maintain with a paper cylinder that you can see here. And we used different masses of talc and different wind conditions. So we investigated the dispersion under a stable atmosphere, under a wind of 3 meters per second and 5 meters per second. We measured the dispersion using a high-speed camera that we can set on the side of the wind tunnel, but also on the ceiling to have a top view of the dispersion. And we used the frequency of almost 11 kilohertz. And we triggered the high-speed camera using the firing system of the impulse of the detonators. So we also used the light spot in order to illuminate the dispersion. So we put this light over the high-speed camera, and we conducted a preliminary investigation using a laser sheet in order to see inside the plume. And in that case, we put the laser sheet coming from the top. So to reproduce the explosive source, we used 2 explosives, so 2 detonators, RP80 and RP83. So they are gram scale detonators. You can see a picture here of one. And we measured the pressure wave generated by the explosion, so the blast, via pressure sensors set flush to the surface of the test table. And we held the pressure sensor using an elastic system that you can see here in order to remove the noise due to the vibration of the test table. And we measured the pressure using a sampling frequency of 8 megahertz. So here are two examples of images of the dispersion that we obtained. So on the left, you can see the dispersion in free field under a wind of 5 meters per second coming from the left. So this is slow motion, of course. And here you have a top view of the dispersion inside the T junction. So now about the methodology. First, we characterized the explosives that we use and then the dispersion. So to characterize the explosive, we usually use the blast wave generated by the explosion. So the blast wave can be compared to an acoustic wave that is better known in general. So here you have a general shape of an acoustic wave. So an acoustic wave will propagate at the speed of sound, and the variation of pressure are really small. To give you an idea, the sound of a trumpet 0.5 meters away from the trumpet is around 0.63 millibars. On the opposite side, here is a general shape of a blast wave. So a blast wave is composed by a really fast increase of pressure, so fast that in theory it's a discontinuity of pressure, followed by a positive pressure phase called compression wave, and a negative pressure phase called rarefaction wave. So the blast wave is propagating at a speed higher than the speed of sound, sometimes 2 or 3 times higher, and the pressure involved in the blast wave were higher. So usually we use some threshold in order to predict the consequences of a blast wave in urban environment. And to give you an example, the threshold for broken glasses is 20 millibars. So 20 millibar here, pressure step. And 50 millibars is the threshold for the eardrum perforation. So to characterize a blast wave, we use usually the pressure peak here, delta P, the positive impulse, which is the integral of the compression wave, and the arrival time of the blast wave. So as said before, we use the blast wave in order to characterize the energy of the explosion. And to do so, we will compare the characteristic of the blast wave with the one generated by 1 kilogram of TNT. So to do so, we use reference curves based on 1 kilo of TNT. And we will compare the characteristic of this blast wave with our blast wave. So here you have reference curve of the 1 kilogram of TNT for the pressure, so the variation of the pressure regarding the distance and the variation of the positive impulse regarding the distance. So we will compare the characteristic of our blast, and thanks to that, we will obtain a TNT equivalency of our explosion, which is the TNT mass needed to reproduce a similar explosion than the studied explosion. So here are examples of pressure signal that we acquired in the lab. So at different distance from the explosion, so 350 millimeters away from the explosion, 725 millimeters, and 1,250 millimeters away from the explosion. So as you can see, the pressure peak here decreases exponentially with the distance and the time. On the opposite side, the duration of the positive and negative phases increase. So we measured the pressure and the positive impulse of the blasts produced by our two explosives, and we compared it to the TNT reference curves. And thanks to that, we could estimate the TNT equivalency mass, so the mass of TNT needed to reproduce the same explosion for the two detonators. So for the smaller detonator, we reached a mass of 0.136 gram of TNT. And for the stronger one, 1.31 grams of TNT. And as we are investigating the phenomenon in real scale, at a scale of 1 to 200, this mass represents actually in real scale an explosion between 1 to 10 tons of TNT. So now that we have characterized our explosives, we can characterize the dispersion. To do so, we actually processed the dispersion into following three steps. So the first step consists in extracting the contour of the plume. So this will lead to information about the position of the barycenter of the plume, the variation of the area of the dispersion according to time, and the expansion velocity of the plume. Then we extracted the velocity map of the dispersion using the large-scale particle image velocimetry, a technique that I will describe later. And then we applied the Misleading Technique in order to obtain the powder distribution of the dispersion. So in order to extract the contour of the plume, so we developed a code on MATLAB, a really simple code where we first remove the background of the experimental image and we increase the contrast. And then we binarize the clouds using a dynamic threshold based on the luminosity of the clouds one image before. Finally, we crop the image and we can obtain the contour of the plume. So in our case, the use of the dynamic threshold is really important because as the dispersion continues, the plume will get more and more diluted, and then the threshold needs to be changed. So from the contour analysis, we can obtain the barycenter of the plume. So then an information about the mean position of the plume according to time. We can access the area of the dispersion and the contour expansion velocity. So to access the contour expansion velocity, we just suppose that at the first moment of the dispersion was hemispherical. And then we compared the contour at time 1 and time 2. We could estimate a mean contour here, and then we could estimate the velocity expansion for each analyzed dot. Then to access the velocity map, we applied a technique called large-scale particle image velocimetry. So the large-scale PIV is based on the same principle than the standard PIV, usually used in experimental fluid experiments. So to simplify the technique here, you have an experimental image of PIV, typical to PIV analysis, where you seed the flow with particles. Usually it's all particles. And to simplify the technique, actually you follow the movement of the particles between two images, and you use these two images, you do a cross correlation between small windows of these two images. Here you have an example of the cross correlation matrix that you obtain, and you detect the peak of correlation of this matrix, and this will lead to the displacement vector between these two images. So when the flow is too large or the camera is too far away, actually we cannot observe the particles anymore, but we observe the movement of structure. So you can see here a typical large-scale PIV image. So actually the flow contains the same oil particles, but the camera here is farther, so we cannot distinguish each particles. But so instead of following the movement of particles, we will follow the movement of structure. So if we apply the cross-correlation on these images, we can obtain this kind of cross-correlation matrices. So the peak is way larger, but we still have a peak, and actually we can, this is linked to the displacements, the velocity map inside the flow. This large-scale PIV technique has been used in the literature, but we couldn't find really a paper validating the technique. So before applying to the explosively driven dispersion, we first validated the technique using a jet that is better known in the literature. So after validating the method, we could apply it on the explosively driven dispersion. So here you have an example of the experimental images that we obtained. So we lighted the plume using a laser sheet coming from the top, because PIV images are illuminated by a laser. So we started with that. And we applied the Lashkin PLP technique, and we took the mean velocity of the plume to plot it here. So here you have the variation of the mean velocity according to time for the dispersion under no wind in red and under a wind of 5 meters per second in blue. And here you have the velocity map resulting from this analysis. So we can see here that the velocity decreases exponentially with time. And we had to use 2 different frequencies in order to analyze the displacements. So a high frequency to process the high velocities and a lower frequency to process the slow displacements. And we could observe a good connections between the 2 curves. The problem of this technique is that, first of all, it's really difficult to set up. Because of the explosion, all the setup is vibrating, so it's difficult to have a stable laser sheet. And also, due to the high concentration of talc particles here, the laser is not powerful enough to go through the plume. So we have only half of the dispersion. And the fact that we have laser power that is not strong enough, we are also limited by the acquisition frequency. So the maximum acquisition frequency that we could use was 2200. So instead of using a laser sheet, we tried to use a spotlight over the high-speed camera in order to illuminate the dispersion. So here you have the experimental images with the laser sheet that we will call transversal visualization. And here you have the global visualization where the plume is actually lighted by a spot. So thanks to the increase of luminosity, we could reach an acquisition frequency of a bit less than 11 kilohertz. That is way better. So we tried to apply the large-scale PIV on this plume and compare it with this visualization. Here are the results. So in full line, you have the mean velocity of the plume from the global visualization, and in dot line, the transversal visualization. So again, in blue is the dispersion under wind of 5 meters per second, and in red under calm atmosphere. So we could see a good coherence between the 2 visualizations at the end of the dispersion, but we could also observe that the global visualization tends to underestimate the velocity at the beginning of the dispersion. And this is due to the fact that the dispersion at this moment is really too small and compact to be analyzed by the global visualization, and we have really 3D component that is too strong. So to complete the data here, we decided to use the contour expansion velocity. So here you have an example of the velocity we obtained at the first millisecond of the dispersion. We took the mean velocity, and as you could see, the mean velocity fits well with the transversal visualization results. So we decided to use the contour expansion before 10 milliseconds and after to use the global visualization after this time, which is experimentally way easier to set up than the transversal visualization. And finally, we used the misscattering technique to access the concentration field of the dispersion. So the misscattering technique is based on the principle that in some conditions, the scattered light of a flow is directly linked to the concentration of the particles inside the flow, which scatter the light. So this means that from an experimental image that you can see here, we can retrieve a concentration field. The absolute concentration value is usually difficult to access because it requires a really heavy calibration. But an absolute value, it's more simple to access when a relative value is easier to access when you divide the absolute value by a reference. That is usually the light intensity where the flow is supposed to be at 100% concentrated. So to access the concentration from the experimental image, we just need to take the luminosity of the image, and we remove the background light of the setup. So this image is just taken as the experimental setup without any smoke. And we divide it by the background, the background smoke image, we call it, is actually the light dispersion of the laser sheet. So this is taken usually by filling up the laboratory with smoke and turning on the laser. So we can see really the distribution light of the laser. And we remove the background light to this image. So in order to explain better and to understand better this technique, here is a simple example of the application. So here you have a main image of a subsonic jet filled with smoke. So you have the light intensity map. So as you can see here, you have the exit of the jet. The light intensity increases with the height and then decreases. This is mainly due to the fact that the laser sheet here was coming from the right and centered in the middle of the jet. So the Gaussian of the light was really centered here. So we used the calibration images, so the background light and the light distribution of the laser sheet. So as said before, the background light, we just remove all the smoke of the laboratory to take the picture. And the light distribution, we filled up the area with smoke to visualize the laser sheet. And indeed, we can observe that the Gaussian of the laser light distribution is really focused here. So after compensation, we could retrieve the concentration map of the subsonic jet, where we see that the concentration is at 100% in the all potential cone. That agrees with the theory. So now about the experimental results. So first, the contour analysis. So we could investigate the velocity of the dispersion at the first millisecond of the dispersion. So here we compared the dispersion of 28 grams of talc and 10 grams of talc. And we took the mean velocity of the contour expansion. And we plotted according to time. And as you can see here, at the beginning, the cloud, the plume containing the lower mass of talc propagates the fastest. And after we have an inversion. This is mainly due to the inertia of the plume. And it has been also observed in the literature. The investigation of the expansion of the contour is only consistent until 10 milliseconds, after which the dispersion is not hemispherical anymore, so we cannot use this method anymore. So after this time, we use the Lashkin PLP. So here we investigated the dispersion of 28 grams and 10 grams of talc under no wind and under a wind of 5 meters per second. As said before, at the beginning we have an underestimation of the velocity, so we will use the contour expansion velocity to have the small time just after the explosion. And here we can observe that before 30 milliseconds, actually, the effect of the mass of the powder is predominant on the dispersion. We have a similar dispersion with a similar mass of talc. And after couples of milliseconds, here approximately 100 milliseconds, actually it's the atmosphere condition that will lead the dispersion. So we see really a similar dispersion with similar atmospheric conditions. We conducted a similar investigation. So here for 3 different wind speeds. And as observed before, we can really see a similar dispersion at the beginning. So no effect of the wind, no strong effect of the wind. And after around 100 milliseconds, we can see the dispersion that stabilized to the mean velocity. We used the velocity map also to investigate the velocity profile of the dispersion at different time. So to do so, we just took the dispersion and we took the minimum, the mean of the velocity for each height. So we took the mean horizontal component and the mean vertical component for each height, and you can see it here. So the dot line are the vertical component of the velocity and the full line, the horizontal component. So the first thing we could observe is that the vertical component is not really affected by the velocity of the wind. On the opposite side, of course, the horizontal component is highly affected by the wind. So, of course, the dispersion under no wind has a null velocity, horizontal velocity. And we see from around 150 milliseconds after the explosion, the atmospheric boundary layer shape that is starting to appear on the velocity profile. So we also investigated the effect of urban configuration on the dispersion. So here you have an example of a T configuration. So we investigated the effect of the wind. So here the wind is going on the same direction than the main street. And as you can see at the beginning, the dispersions are really similar. And at one point you have the dispersion under wind that will keep its velocity and will be faster than the dispersion under no wind. We also investigated the effect of the direction of the wind. So here is the wind on the same direction than the main street, and here a parallel wind. And as before, we could observe that the dispersions are really similar at the beginning, but after we could observe that the presence of wind on the parallel streets will actually slow down the dispersion. So finally, the mis-scattering technique. So this work is still ongoing because we had to face many issues. While the mis-scattering technique was working well on a jet, it was way more difficult to apply on the explosively driven dispersion. First of all, because of the concentration of the talc particles. So as said before, the plume was too compact to let the laser sheet going inside the plume, because the mis-scattering will really need a laser sheet. So we decided to reduce by 20 times the concentration of the talc, and even using 0.5 grams of talc, the plume was still too compact at the beginning of the dispersion. And after around 200 milliseconds, we could have actually a nice odor distribution visualization. But another issue that we had is the visualization of the light distribution of the laser sheet. So here is an example of the image that we obtained in the laboratory. So we couldn't visualize the light distribution, mainly first of all, because of the power of the laser that is not powerful enough. When we study a jet, the area is small, so we have a high power of the laser. But here we had almost 2 meters of investigation, so we had to have a really wide laser sheet, which reduced a lot the power of the laser. And also, to visualize this, we used smoke that reflects way less light than talc. And the camera here was really calibrated for the light intensity of the talc. That's mainly why we couldn't see well the light distribution. So without the light distribution, we couldn't really access a concentration map of the dispersion. However, we could already appreciate the powder distribution of the plume and have some conclusions. So here, for example, you have the dispersion, the luminosity map, so the powder distribution map of the dispersion at 20 milliseconds for the RP80, so the small explosive, and the RP83, the stronger explosive. And as you can see, the small explosive will lead to a plume that is way more compact. That for the safety is way more dangerous. We also investigated the effect of street on the dispersion. So here you have the dispersion in 3 fields, and here actually we added some plexiglass walls to reproduce a straight street. You can see here actually the shape, the end of the plexiglass wall. So we could really see here that the presence of street will lead to a way more concentrated plume up over the explosive. So for this technique, I think we still need we need to work on that. Still, we need or a more powerful laser or a smaller studied area, and maybe we need a lower particle density, which may be experimentally really difficult because we reach already 0.5 grams. And we really need to access these calibration images to have the laser light distribution. So about the application of these techniques on other challenging flows. So the experimental techniques that we are using here are really made for large dynamic range flows. And they have as advantages, first of all, they require only one optical access. And it's a non-intrusive technique. So it's a really great advantage if you deal with explosives or fire or all these complex flows. And it can solve a large interval of velocities because you can change the time between 2 images, and it can solve large flows that we cannot do for standard PIV. So we can apply these techniques on the other large dynamic flows, such as the decomposition product of a detonation, which is usually really large. The investigation of a fireball, so the luminosity variation and the size variation. And in that case, at VKI, we applied this technique to investigate the supersonic jet. So you can see here the experimental image that we had. And thanks to the technique, we could actually access the velocity map and the concentration map of the jet up to 1 meter away from the exit of the jet. And here, for example, you have the effect of cross flow on the jet. Finally, conclusion. So we investigate the explosively driven dispersion. We developed an experimental setup for small-scale investigations inside the subsonic wind tunnel, and we validated the Lashkin PLP technique for the large dynamic range flows. We are really close to do it also for the misscattering technique, but we still have to work a little bit on that. And yes, we investigated the dispersion under urban and atmospheric boundary layer. So we could really investigate the effect of the plume inertia, so the effect of the mass of the powder on the dispersion. And we could really see the transition between the buoyancy phase and the neutral dispersion, which was at around 100 milliseconds. And the experimental database that we have now will be used to validate future simplified model on the explosively driven dispersion. So as a perspective, as I said before, we need to improve this misscattering technique for the explosion. I think the key will be the calibration images. And we can maybe investigate other measurement techniques for the concentration, such as the light-induced fluorescence technique or the backlighting technique. And we need also to investigate the dispersion inside a more complex urban configuration. So we did other tests. For example, this configuration that is more complex configuration with an effect of shallowing here, a U configuration. You can see here the resulting dispersion that is really interesting, and it seems that many nice phenomena occurs. So, and finally, we need to compare the experimental data with the numerical models that will be developed in the future. And thanks to this model, we could also investigate the scale effect, because now we are still in reduced scale, and it's really hard to predict what would be in real scale. And we can investigate more energy of explosion and more type order using this numerical model. So finally, I would like to thank the Commissariat à l'énergie atomique et aux énergies alternatives in Karman, who founded this project, and the Université Libre de Bruxelles and the Van Karman Institute for Fluid Dynamics, who hosted the project. Thank you very much. If you have any question, I will be happy to answer.
Thank you. Thank you so much for such lovely presentation. Very, very interesting. I kind of like your parrot run away from the explosion. It looks really great. Well, I have two questions here from YouTube that I will ask you. So the very first, actually I have the text, and it goes like this: "Hello, Charline, congratulations for your work. It is very interesting.
Thank
the
you.
course of accidental explosion that escalates to detonation is indeed a major concern when it comes to its destructive potential." And then comes the question. From what I understand, your work is concentrated in materials that are likely to detonate right away, such as ammonium nitrate. Can your work be applied to flammable gas explosions that can transit to detonation because of the presence of congested areas? If you want, I can read that again. It's quite long.
No, that's okay. Thank you. Yeah, I mean, my work is really focused on the condensed-phase explosion, so a solid explosion. But then the gas explosion, if you have the transition, is really not the same phenomena. And here we are investigating the dispersion. So I think I mean, maybe it can be applied, but you need to think more about it. It's not directly applicable.
Yeah. Well, there's another one here which says, "I've noted that you took into account the influence of the wind and also of the atmospheric boundary layer. Thus, the presence of buildings can affect the turbulent field generated and hence the dispersion of particles."
Yes, of course. It affects a lot. We didn't really focus on that, but indeed, like inside a straight street, you have the canyoning effect that affects a lot. We see it a little bit if I go back here. So here, indeed, it's something I would like to investigate, but with the wind parallel to the main street, we could see really here some canyoning effect. So, of course, the turbulences due to the configuration will affect the dispersion, yes. But maybe not at the first millisecond. This is what we wanted to study. I think at the first millisecond, really, the dispersion will be just led by the explosion. And after, yes, of course. It will be actually really interesting to study first the flow field inside the configuration, and then investigate the dispersion in this flow field to see a bit the effect of the explosion and the dispersion itself.
There's another one here that says, "We know that the main level of damage produced in an explosion is due to overpressure produced. However, did you get the chance to investigate effects due to thermal radiation?"
No, we didn't study that. Because as I said at the beginning, the radiation actually will be really reduced by the presence of building. Yeah, we needed to focus on some phenomena, so we decided the dispersion and the blast. it can be a problem, but in far fields, it's less a problem than the blast wave and the dispersion.
Yeah, absolutely. Yeah. One of the things that, just a small comment as well, is that the time scale on the heat transfer in that case is completely different. So that would be probably another issue. Well, there's loads of questions here, right? You should be ready. Okay. Detonations have really high damaging effects. However, they are not very likely to occur in urban environments due to the presence of industries. Is your work mainly motivated by terrorist attacks?
Well, I disagree with that because it's mainly the actual problem that before we were constructing some industrial plants and the urbanization, the houses get closer and closer. So we had really a lot of examples of big explosion inside the city center, like Beirut, like Azadef in France. And it's like this will cause the highest damages. So of course it's also motivated by the terrorist threat because it's really a threat, like also a chemical attack. But the industrial accident is really a threat. It happens more often than it should be.
Yeah. One of the things that I would like to add as well is that we never expected to have a detonation, let's say, that likely, but after Buncefield, I think Buncefield is a very good example that we experienced a level of pressures, particularly for a storage area that we were not expecting that in the first place. But at the end of the day, the structural evidence, they are quite strong that we end up with very, very high level of overpressure, probably created by those bushes and stuff like that. But anyway, yeah, I agree with you. There's one more question from the YouTube, which says, and actually that's one of the questions that I have myself, more or less in the same direction. The gentleman or the lady is referring to slide 30. In my case, it's slide 27, but they go together somehow. So the question is, in terms of, as far as the velocity is concerned, you have mentioned a technique to calculate the contour velocity, but could you clarify which axis did you use to calculate the previously mentioned velocity? So that's specifically for the slide number 30. And,
yes. So
let me take the chance as well. And my question is, once you have addressed this, if you go to the slide 27, and if you clarify how do you calculate the velocity itself, that was not very clear to me as well. So 2 questions in one.
For the contour expansion still, right?
Okay. Yeah, the first, the contour, yeah.
Yeah, so we just here suppose that it was in 2D. We know that it's not 2D, but we just investigate it here in 2D. After, indeed, you have an image here where you have a velocity component here that goes down. This actually is the plume that is going toward the camera, and we didn't take it into account in the mean velocity. We took only this velocity. So indeed, here the expansion velocity doesn't represent fully the full velocity inside, but it's a good approximation. And for your question, then
for my question, what I could understand is that the lines I see on your plot, they are average values from the vectors that you observed. Right?
Yes.
And they are, they are the cutting edge of, if you think of the flame, if you have the flame front which propagate, in your case you have some sort of powder which is propagating with the explosion. So that velocity tries to measure how that powder is propagating. Is that what it means?
Yes. When you check, do I have a velocity map? Yes, I have for the transverse. An approximation of the velocity that we obtained. And it's really like, yeah, the velocity in each little zone. that we averaged. So at the beginning, of course, is a symmetrical dispersion. So you will have an expression, and after the dispersion will follow the wind. So you will have all the vectors that will follow the wind direction, as you can see at the end. So yeah, we took the mean velocity of the plume itself.
Okay, there's one more here from YouTube as well. So that goes for slide 39. So the question is the wind slowing down the dispersion, or the difference is due to the acceleration of the y velocity with parallel upward wind? Do you want me to say that again?
If I understand well, the question is this slowed down or this accelerated, basically, right?
Well, no, it says, is it slowing down? So that would be the effect due to the wind, or the difference is due to the acceleration of the y component. Yeah.
Yes, so maybe I should have compared this with a dispersion without wind. We see really the dispersion stopping here. So really, the wind has a strong effect on that.
Yeah. Well, you know what? When I first saw this slide, I would expect your plume to go through and then bend to the right a little bit. I wouldn't expect it to stop there unless the momentum of the plume is so low that the wind momentum is kind of pushing back. It seems that it gets stuck there, right? It doesn't go to, I would expect to go through and then bend to the right. That's something interesting. Okay.
Yeah.
Yeah, go ahead.
It's a really interesting phenomenon, but yeah, I would like to study it more, but for now I didn't have the time. So, yes.
I have a couple of other questions here. You know, at the beginning of your presentation, you did some comparison, or at least it sounds to me as if you're trying to tuning your model or your data based on the TNT model. And then on the TNT, you need to come up with these efficiency factor, which is quite challenging. So could you comment a little bit on that? How did you come up with the eta, which is this efficiency factor for the TNT model?
Yes. Actually, I didn't describe too much because, yeah, I didn't have so much time. But this technique is usually used when we deal with explosives. We like to have a mass of TNT for each explosive because the TNT is maybe the best known explosive. We studied it a lot in the past. So we tune it. Yes, actually we use the scaling law for explosive. So Hopkinson scaling law. So we have these curves and we divide the distance where we measure the blast by the mass of TNT equivalent, power 1/3, and also the scaled impulse. And this is basically using the scaling law, saying that if you divide by the mass equivalent of TNT, you have normally a superposition of all the data. In reality, it's not really correct. It doesn't work really well, but it's a first approximation to understand the propagation of sound blast.
I see.
So basically, yeah, we took the blast characteristic and we divided by a mass leading to a superposition of the dots with the reference curves.
In terms of the PIV approach, the cost correlation, did you, at the end of the day, do you guys develop your own code? Do you just use the cameras and the laser and develop your own code, or use any particular package?
No. This code, I mean, is the regular PIV code. So it's just a cross correlation of the image. So it's really simple. Depending on the analysis, I think for the supersonic jet, we use the system of Davis. So with the PIV code included. And for the explosively driven dispersion, I think I've tried with a code on MATLAB called PIV lab that works also well.
Okay. Yeah.
So no need to develop a code. It's really the code used for PIV.
Okay. Now, I have one more question, maybe the last one, and it might well be that the most difficult question of the afternoon, I'm not sure, which is how many times did you run your experiment in order to get your results?
Yes, so each result that I show, actually I based on one test. All this is not an average on many because we are really limited by the number of explosives that we have. Yes. After, I didn't show it here, but we made sure that each test had a good repeatability. So we tested the same configuration many times, 3 times. And we had approximately the same results in good order of magnitude. And we checked also, actually, we measured the blast generated by the explosion on each test. And we know that the powder really impacts the blast. If the powder is not well distributed around the explosive, we will have a non-symmetrical blast. So by measuring the blast and comparing for each test, we can make sure that the powder was exactly the same every time in every configuration. So we can assure the repeatability a bit more, let's say. But we cannot afford to do 10 tests every time, unfortunately.
Yeah. Let me ask you one thing out of the curiosity. When you run for the very first time, very first time, were you concerned that you could blow it up, the wind tunnel or something like that? I mean, how confident were you that things would be under control?
No, of course, the wind tunnel of DKI is it was the biggest. I think it's still the biggest in Belgium. So no, they didn't let me do the explosion directly. We first of all, we were not really trained for explosives, so we went to a military field and we were trained by a specialist on detonation. And then we measured the blast in free field outside to be sure that inside the wind tunnel, the wind tunnel will resist the pressure level that we will have inside. So no, we didn't go directly. We made sure before that we wouldn't explode everything.
Yeah, well, that was fantastic. Well, I think we're running a little bit late today. I mean, we don't have any more questions from the YouTube. I think what I want to do is to thank you so much for accepting this, to share with us.
Thank you very much.
All this work, this fantastic work. I'm very glad. I remember that maybe a couple of months ago, Delphine was delivering a very good presentation as well, and with the same standard of quality that you did, which is fantastic. And thank you again for that. And I hope that next time we have the chance to meet face by face, and all this pandemic phase that we're going through, it's going to be gone. I think the whole world is really looking forward. So, and again, Charline, thank you so much. Thank you for your time. I take this opportunity to wish you a lovely evening back in Europe. We still have a few hours in the day here to go. Thank you so much. Bye.
Thank you to you. Have a good afternoon.
Thank you. Bye-bye.